This video covers sections STSD C to E. To begin, let's look at the definition of variance and standard deviation. Now, to further describe data sets, measures of spread or dispersion are used. One of the most commonly used measures is standard deviation. Now, the standard deviation gives more information on how the values of the data set are varying or deviating from the mean of the data set. Deviations are calculated by subtracting the mean from each of the sample values. So you can see that there. For values less than the mean, you'll get negative deviations, and for values greater than the mean, you'll get positive deviations. So by simply adding the values of the deviations from the mean, the positive and negative values will cancel to give a result of 0. By squaring each of the deviations, the problem of the positive and negative values cancelling is avoided. So to calculate the standard deviation, the deviations are squared. These values are then summed and divided by the appropriate number of values, and then finally the square root is taken of this result. That's to counteract that initial squaring of the deviation. So calculating the standard deviation of a population, we use sigma notation for that, for a population. So if we have n data values, we have the formula here. So the standard deviation is a square root of the sum of x minus the mean, or squared, all over n, where mu is a population mean. If we're looking at samples, then the sample of n data items, the standard deviation, little s, is going to be given here. So you can see instead of using mu, we're using x bar. Now note, when calculating the sample standard deviation, we divide by n minus 1, not n. So if I go back to the previous slide, you can see that we divided by n here, and that was for the population standard deviation, where we used the population mean. If we're looking at our sample, we're using n minus 1 and our sample mean. Now, standard deviation is measured in the same units as the mean. It is usual to assume that the data is from the sample unless it's stated that it's a population. So just assume we're talking about samples all the time unless we say otherwise. To assist in calculations, data should be set up in a table and the following headings should be used. So you've got your x value, you'll have x minus mu if you're talking about a population, or x minus x bar if you're talking about a sample, and then you have to square whatever the values are. So let's look at an example. Determine the standard deviation for the following student test percentages. So I have my x has been filled in. To find out what x minus x bar, I need to work out what that mean is. So the first step there is to calculate the sum of x, and in this case it's 784. So our mean is the sum of x over n, so 784 divided by how many results? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So divided by 11 and you get approximately 71.3. So then we come back to our table and we're going to have 92 minus 71.3 and you'll get 20.7. Square it straight away because then it's already on your calculator, so if you're not getting an exact result, you can just square straight on your calculator and use your previous answer and you get 428.49. Okay, here you're going to have 66 minus 71.3, so this is going to give a negative 5.3, but when you square a negative, it becomes a positive. Okay, here you're going to have 99 minus 71.3, which will be 27.7. Then we square it, and you get 767.29. So you can see that I've gone through and entered all that data that is in your textbook. I need to find the sum of those deviations. So adding all this column up, I get 2978.19. So my standard deviation, write out my formula. Now these formulas, you don't have to memorize them. They'll be given in any test that you do. Now we plug in our value, so 2978.19 all over n was 11 minus 1. So that ends up, if you plug it on your calculator, approximately 17.26. Now let's look at variance. We're going to look at population variance and also sample variance. The key here is that variance is just a standard deviation squared. So if you look at these two formulas here, they're exactly the same as what we had for standard deviation, which had a square root sign. We just get rid of that because we square them. Okay, nothing more than that. Now, as variance is measured in squared units, it's more useful to use standard deviation, the square root of variance, as a measure of dispersion. So we very rarely use variance. Now let's look at another way of calculating standard deviation. This is how we previously calculated it, by finding the difference between our score and the mean for each different one, squaring it, etc. Now we can manipulate those formulas to get these two here, and these are much easier for calculating. It's a much quicker method than trying to find the deviation from the mean every time. Now again, these formulas will be given to you so you don't need to remember them, and the headings that we need in our table are x and x squared. If we have those two headings, we have everything that we need for that formula. So let's look at an example. Determine the standard deviation of the following student test percentages. So firstly we go through and find out what x squared is in each case. So with the first one we've got 92, so 92 squared gives me, so what we do is 92 squared, and that gives me 8464. Then 66 squared gives me 4356. Okay, so I've gone through and filled in those values all the way down, so just squaring each x term. I also need to sum each column. The sum of x is 784, and the sum of x squared is 58861. Sorry, 8856. Suffering a little bit from dyslexia. So 58856. So now we write out our formula. Sum of x squared minus the sum of x all squared all over n, that's all over n minus 1, because we're looking at sample. Plug in what I've got. So the sum of x squared is 58856 minus the sum of x was 784, and I need to square it. That's all divided by n, and there's 11 scores, all over 11 minus 1. Okay, now you might want to just plug that straight in the calculator so you're not estimating an estimate. And when you're plugging it in, start with it. So I'm going to go through it here with you. So it's 58856 minus, then it's 784 squared divided by 11. Press enter now, or equals on your calculator, because you want to evaluate this whole top thing before you divide by what's on the bottom. Okay, so press enter and then divide that by 10. And then just press your square root button, and hopefully you've got an answer button on your calculator, so that'll just plug whatever the answer was straight back in, so you're not approximating twice. And you'll get approximately 17.26. Okay, now we are looking at percentages, so therefore the standard deviation is approximately 17.26%, has the same units. Next, calculating standard deviation from a frequency distribution table. And again, there's just a formula, and you're given these formulas. So as long as you can work out what everything is that's in the formula, you just plug it straight in. Now, if the data is presented in a group or interval manner, you still need to work out those mid values, which we've also looked at. And our table headings are going to be these ones here: x, f, fx, x squared, and fx squared. So let's do an example. Here I have calculate standard deviations for each of the following data sets. First of all, number of pins knocked down into 10 pin bowling matches. So here's my x and here's my frequency. So fx is going to be 0 times 2, which is 0. My x squared is going to be 0 squared, which is 0. My fx squared is going to be my f, 2 times by my x squared, which was 0, which is 0. So let's do that again. F times f is 1 times 1, which is 1. X squared is 1 squared, which is 1. F times x squared is 1 times 1, which is 1. Do the next one, fx. 2 times 2 is 4. X squared is 2 squared, which is 4. F times x squared is 2 times 4, which is 8. Okay, so I've gone through and filled in all those values. I need to sum my frequency because that's what's in my formula, so that's 60. I need to sum my fx column, which gives me 420, and I need to sum my fx squared column, which is 3,284. I then write out my formula, and I suppose the biggest mistake you can make is writing it out incorrectly. So the sum of fx squared minus the sum of fx all squared all over the sum of f all over the sum of f minus 1. So plug in what we've got. 3,284. So that's this value is the sum of fx all squared. Then we have the sum of fx, which is this one here. So we have minus 420, we need to square that, all over the sum of f, so that's this value here, is going there, which is 60, all over the sum of f, so 60 minus 1. Plug that in your calculator, you can get approximately 2.41. So therefore, standard deviation is approximately 2.41 pins. Here's one for you to do. What I want you to do is go through and try and do this for yourself. Firstly though, you need to find your midpoint. Okay, so this value here. Now remembering that for this value here, it's 140 plus 145 divided by 2, which gives us 142.5. So go through and give this one a go first. Okay, so hopefully you've given it a go. I've just filled in all my x terms. Now I'm going to fill in my fx, and I'm just going to explain the first row so you can make sure what you've done is correct. So fx is the x times the f. So 142.5 times 1 is 142.5. X squared is 142.5 squared, which gives me a huge number. Then fx squared, so that's my f times my x squared. So 1 times that gives me the same thing. Okay, I'll do one more. So fx, so 1 times 147.5. X all squared is 21756.25. And then f times that is 21756.25. So if you haven't completed it yourself, pause, do it yourself. Okay, so I've gone through and filled in all the table. I've also summed the columns that I need for my formula. Okay, so I'm going to delete this, so I've got some room to work out my standard deviation. S equals, write out my formula. So make sure you don't make a mistake here. I think you'll agree. The calculations are the most tedious part of this. You know, not adding something correctly or writing the formula down incorrectly. So now plug in what I've got. Make sure that square root goes over the whole lot. So I've got 518,325 minus 3215 all squared over 20 all over 20 minus 1. Again, you can see my square root sign isn't big enough, so I'm going to make sure that's bigger. Plug that into your calculator and you get 8.93. Finish with a therefore statement. Therefore, standard deviation of heights is approximately 8.93, and doesn't have units, but I'm going to assume it's centimeters. Okay, if you wanted to, you could stop the video now and go and do some exercises in the textbook, but I'm going to do the one more thing so then you can go and practice it all. So coefficient of variation. Now without an understanding of relative size of the standard deviation compared to the original data, the standard deviation is somewhat meaningless for use with a comparison of data sets. Now to address this problem, we use a coefficient of variation. Now the coefficient of variation, or CV, gives the standard deviation as a percentage of the mean of the data set. And you can see that here. So it's standard deviation over the mean times by 100. So quick example, calculate the coefficient of variation for the following data set, the price in cents of a stock over trading days. Okay, and it gives us the data. So our first step here is to calculate the standard deviation. Okay, we also need our mean to be able to do that. So try and go and fill this table in first. Press pause. Okay, do it yourself, then come back to it. Okay, so you can see I've filled in my table. So from there, my mean is the sum of x over n. So 281 over 5, which is 56.1. My standard deviation is the sum of x squared minus the sum of x all squared all over n minus 1. So that becomes square root of 15823 minus 281 squared all over 5 minus 1. Plug that in your calculator, you get 2.77. So my coefficient of variation is my standard deviation over my mean times by 100. So that's 2.77 over 56.1 times by 100, which is approximately 4.93%. And you would finish with a therefore. Okay, it's written in your textbook, but it says coefficient of variation of the stock prices is 4.93%. So therefore, you can say that the prices haven't shown a large variation over the 5 days of trading because it's quite a small percentage. One more example, which is comparing the variability of data sets. The coefficient of variation is often used to compare the variability of two data sets. Now it allows comparison regardless of the units of measurements used for each data set. So the larger the coefficient of variation, the more data varies. So here we have the results of two tests as shown below. Calculate or compare the variability of these data sets. So we know that our coefficient of variation is our standard deviation over our mean times by 100. So in this one we're going to have 2 over 9 times by 100, which gives me approximately 22.2%. For this one I'm going to have 8 over 27 times by 100, which is approximately 29.6%. So you can say here this is a high percentage, so therefore second set or test 2 has greater variation. Okay. This is a long video, I apologise. But, you know, we're covering a lot of things. Again, remember you can pause and come back to videos. You don't have to watch the whole thing at one go. So what now? Complete exercise STSD D1 and STSD E1. So it's only 2 exercises on all of that.